When a massive short circuit strikes a high-voltage power system, the result is instantaneous and violent. Millions of watts of energy look for a way out, tearing through industrial metal and superheating the surrounding air into plasma. But if you open a standard electrical engineering textbook, you won't see that chaos. You'll see this, a perfect AC sine wave, undulating in a clean, predictable rhythm. But if a power grid's safety systems assume fault currents maintain this perfect balance, defenses fail. A real-world fault effortlessly bypasses them to collapse the equipment. Actual electrical surges are inherently lopsided. They generate hidden, uneven forces that require a much deeper understanding of physics to predict and survive. This IEC schematic shows the true shape of a short-circuit current. Instead of oscillating evenly, the wave is initially pushed heavily to one side. Notice the central dashed line curving downward. This decaying DC offset physically shifts the alternating current off its center axis. This offset creates a massive gap between textbook predictions and what the hardware actually experiences. It turns a standard symmetrical surge of electrons into a mechanical hazard capable of tearing a substation apart. To prevent that destruction, engineers have to look at the grid's basic physical properties to understand why it generates this distortion in the first place. Think of phase timing like pushing a heavy metal pendulum. If you apply force at the correct point, you get smooth, continuous motion. But if you strike it at the wrong moment, the pendulum violently jerks against you. A modern power grid operates on a similar principle, but the weight is electrical. The system is packed with massive wire coils inside generators and transformers, creating a highly inductive environment. These inductors store energy in magnetic fields. Because of that stored energy, they physically cannot allow the flow of electrical current to change instantaneously. They resist sudden shifts. When a short circuit hits at an unfavorable point on the voltage wave, the current wants to jump instantly to a massive new value. But the system's heavy inductance steps in, choking that impossible jump. To satisfy the laws of physics, the grid mathematically compensates for this disruption. It generates that temporary DC offset, shifting the wave to keep the current continuous and prevent an impossible physical leap. The grid's physical response boils down to a single equation. Total fault current is the sum of two parts, steady alternating current and direct current offset. The DC component represents the grid bleeding off trapped magnetic energy, clearing as the magnetic fields collapse. The speed of that burn is determined by the system's X/R ratio, the ratio of reactance to resistance. This acts as the grid's internal braking system, turning that trapped magnetic energy into heat. Going back to our IEC schematic, look at the right side of the timeline. The DC offset eventually flattens out to zero. At this point, the alternating current settles into a symmetrical, steady-state short circuit. The offset eventually vanishes, but those first few milliseconds dictate whether the grid infrastructure remains intact or suffers a total cascading failure. Let's look closely at the hardware during those critical opening milliseconds, right when the DC offset pushes the current to its absolute peak. This extreme, lopsided peak generates immense electrodynamic forces. These forces act like physical weights, capable of warping thick metal busbars and shattering the insulators holding them in place. Amidst this mechanical stress, a high-voltage circuit breaker has to do its job. It must physically pull its massive contacts apart and extinguish a burning plasma arc, exactly when these asymmetrical forces are at their highest. If an engineer sizes a breaker purely on textbook symmetrical currents, the asymmetrical peak will overwhelm the arc chutes. The resulting failure to contain the plasma arc triggers a catastrophic explosion of the housing. Protecting human infrastructure requires abandoning idealized assumptions and calculating exactly how bad the worst-case asymmetrical peak will be. This is where the International Electrotechnical Commission Standard 60909 comes in. It provides the mathematical framework used to wrangle this chaotic, decaying fault physics into safe, actionable data. Standard 6909 defines three metrics. I'(K) sets the AC baseline. IP is the maximum asymmetrical spike, dictating structural strength. IB calculates the exact current when contacts separate, dictating breaker ratings. Unpredictable, violent electrical physics are a reality of the natural world. Standards like 60909 translate those hazards into the precise mathematics required to safely keep the lights on.